Welcome. In this video, we start section 2.3 on mathematical induction. Mathematical induction is a proof technique that is used a lot. It's an interesting idea and very important in mathematics. So we will look at a motivating example, induction, and some more examples. Consider the sequence a sub n defined by an equals an minus 1 plus 2n minus 1 for n greater than or equal to 2, and we have our initial condition that a sub 1 equals 1. Alright, so this sequence is given to us recursively, and I know that it begins with 1. Now how do I read the recursive definition? It says a sub n is the previous term of the sequence plus twice the subscript minus 1. So a sub 2 is the previous term, which is 1, plus 2n minus 1. Now my n is 2, so twice the subscript minus 1, that'll be 3. So I get 4 as my answer. A sub 2 equals 4. A sub 3 is the previous term, 4, plus twice the subscript minus 1. There's my 2n minus 1 is 5. 4 plus 5 is 9. A sub 4 is 9 plus twice 4 minus 1. That's 9 plus 7 is 16. A sub 5 is 16 plus twice the 5 minus 1, so that's plus 9. 16 plus 9 is 25. And do you see a pattern? I'll include the 1 also. I think maybe you do. Make a guess for the closed form of an. It looks like a sub n has such a nice, simple closed form that is simply n squared. So how will we prove that the closed form for this sequence is really n squared? We define the sequence recursively, and we must prove that the sequence has a certain closed form. Here's what we'll do. Here is our strategy. First of all, we'll verify that the claim, so maybe I'll call this the claim. It's really like the definition, this part is defined, and we have a claim part. We have to show that the claim actually holds for a sub 1. And you can see that it does, right? If I plug in a 1 for n, then 1 squared gives me 1, and that matches up with the definition of the sequence. So we verify that a sub 1 really is 1 squared. And now here's the really funny part. I'm going to assume something that's true. I'm going to assume that a sub m minus 1 equals m minus 1 squared for some m greater than or equal to 2. Now, not all m greater than or equal to 2. So I'm assuming that the claim, right, this claim that a sub n is n squared, I'm assuming that the claim actually holds for some particular subscript, m minus 1. In fact, we know that this claim actually holds true when m equals 2, right? We know that it's true when m equals 2. So we don't really even have to assume that the claim is true for some m greater than or equal to 2. We know it's actually true when m equals 2, but maybe it's also true for some bigger values of m as well. Okay? 1, check. 2, check. I've made my assumption. 3, based on that assumption, I want to prove that a sub m equals m squared. That's really kind of funny, right? So basically what I'm doing is I want to show that if a sub m minus 1 equals m minus 1 squared, then a sub m equals m squared. I'm showing that if the claim actually works out for some particular subscript, then the claim is also true for the next subscript. Do you see how that works? So look at this. Retrace the steps 1, 2, and 3. I verify that the claim works when the subscript is 1. I assume that the claim works when the subscript is some m minus 1, and then I prove that if it is true for m minus 1, then the claim is also true for m. And that will show me that the claim is actually true for all possible subscripts. Let's see how that works. So, claim. If my sequence is defined recursively this way, if a sub n equals a sub n minus 1 plus 2n minus 1 for n greater than or equal to 2, and a sub 1 equals 1, then a sub n equals n squared for all n greater than or equal to 1. So proof by induction. We start with something called the base case. This is basically showing that the closed form works when n equals 1. So by definition, a sub 1 equals 1. I'm looking up there for my definition. But also by the claim, if I plug in 1 into my claim, I also find that I get the number 1. These are the same. So the claim works when n equals 1. Now, let's assume that for some particular subscript m minus 1, a sub m minus 1 really does equal m minus 1 squared. And once again, we actually know that this, we just proved on the previous line that it actually does work if m equals 2, but maybe it also works for m equals 3 or 4 or 7 or 19. Assume that it works for some m. Then, okay, what can I do here? A sub m equals a sub m minus 1 plus 2m minus 1. This is just the definition. I've just applied the definition of the sequence. But look, as part of that definition, I have an a sub m minus 1. And now we see why I made this particular assumption. Because I've assumed that m minus 1 is m minus 1 squared. So I can replace that boxed term with m minus 1 squared. That was my assumption. Now let's do some algebra and simplify things. And look what I get. I get m squared. So I had an assumption that the claim worked for subscript m minus 1, and under that assumption, we were able to show that the claim also worked if my subscript was m. So if the claim works with subscript m minus 1, then the claim also works with subscript m. Well, by induction, this actually proves that a sub n equals n squared for all n greater than or equal to 1, because I proved it for subscript 1, and then I showed if it's true for some subscript, the claim is true for the next subscript as well. It's kind of a cool idea, right? Here's induction in general. Let P of n be a statement about the positive integers that we wish to prove. So this could be like the closed form of a recursive statement, P of n. So the first step is I verify that P of 1 is true. So this is what I called the base case. I assume that the statement is true for m minus 1. And then based on that assumption, I prove that the statement is also true for subscript m. If these three things are all satisfied, then in fact the statement is true for all n greater than or equal to 1. For the remainder of this lesson, there are 3 more example proofs that I'll go through. So maybe at this point, if you're feeling okay, you can pause the video and actually try all 3. In the next slide, I'll go through A carefully. But then after that, for B and C, I won't take too much time talking about the proofs. I'll pretty much just put them up on the screen. So do the work beforehand, really try your very best to get those proofs written out, and then you can check your work on the screens for B and C. Okay, let me take some time and we'll look at the first problem. So our definition says a sub n is a sub n minus 1 plus n plus 4 for n greater than or equal to 2, and the first term of my sequence is 5. And the claim is that I have a closed form, that in general a sub n is really n times n plus 9 divided by 2 for all n greater than or equal to 1. So let's see. If I take the recursive definition as given, can I prove the closed form? So by the definition, a sub 1 equals 5. And does the claim actually work if I put in a 1 for n? By the claim, a sub 1, so now I'm looking at the claim part. A sub 1 is 1 times 1 plus 9 over 2. Yeah, oh yeah, that's 5. I see a 5 there. I see a 5 there. It makes me happy. Thus, the case n equals 1 holds. I'm done with the base case. Now I move on to the induction part. Now assume that the claim holds for subscript m minus 1. In short, that's kind of what I say. Let's assume the claim holds for subscript m minus 1. In other words, let's assume that a sub m minus 1 is m minus 1 times m minus 1 plus 9, all divided by 2, for some m greater than or equal to 2. Basically, I just took the claim, and I just replaced the n with m minus 1. This assumption, maybe I'll give that a name here, that's called the induction hypothesis. All right, so now what? So let's talk about a sub m. Well, a sub m equals a sub m minus 1 plus m plus 4. Why is that true? How can I say that equality? Oh, that was the definition. That's the recursive definition that's given to us. But look at this. As part of the definition, it includes a sub m minus 1. Now my induction hypothesis says something about a sub m minus 1. I can take that guy and replace it. So that's what we see in the brackets. In the brackets, I've replaced the a sub m minus 1. Now let the algebra begin. Oh, maybe I should label this by assumption or by induction hypothesis. Maybe the word assumption is shorter. All right, there's just a lot of algebra there, but look at this. By the end of all this algebra, I come up with a sub m equals m times m plus 9 over 2. You know, that's really just like the claim, but with my n's replaced by m's. So in fact, right, if I assume my induction hypothesis, if I assume that the claim works with subscript m minus 1, then I've just showed the claim works with subscript m. This proves the induction. By induction, a sub n equals n times n plus 9 over 2 for all n greater than or equal to 1. All right, now for problems B and C, I said I would just show those, and I will. I won't speak over them, but I'll reveal them line by line, and pause the video when you need to challenge yourself, see just what you need to see, and then try to keep writing the proof and moving on from that point. All right, here we go. I'll just go right through problems B and C. That completes B, and now C. And that's it.